So, good afternoon. So this is the third lecture of the Discrete Lattice model series. In the first lecture, I gave 6 examples of lattice models and one result I thought was interesting about each of them. And the program for the remainder is to study 2 lattice models in somehow more details. Both are critical lattice models. They exhibit long-range fluctuations, and these models have, for that reason, scaling limits. So when you look at really far away from at one of these models, you see a continuum limit. And the goal is to prove 2 results about these models that are interesting in their own right and that are useful to establish the connection between these models and the SLE processes Vincent spoke about. So the model I started the second lecture with is critical percolation on the triangle lattice, which we represent as a critical percolation on the faces of the honeycomb lattice. So what does it mean? It just means that you color each face of this infinite honeycomb grid in either black or white. And I always draw with a white chalk the black hexagon with probability 1/2 independently of the others. Okay. So for this model, I want to give some ideas of the proof of a celebrated theorem of Smirnov, which is the proof of the so-called Cardy's formula. Let me just remind you what we did last time and what is the statement of the theorem we want to prove. So what we did last time was first we proved a preliminary result arguing that the limit that appears in this theorem of Smirnov is at least neither 0 nor 1. And by doing so we proved an inequality called the Russell-Seymour-Welch inequality. And as a corollary of that inequality, we obtained a result, which is an estimate, which is going to be useful today. So let me just remind you what this estimate was. So if you look at critical percolation in an annulus with small inner radius r and large outer radius capital R, the probability of having a path of black hexagons that links the inner circle to the outer circle is less or equal than the ratio of these radii to the power alpha for some alpha positive uniformly in delta, the size of a hexagon. So I state this because it's going to be useful and also because it reminds you what is the notation. So we have hexagons of size delta, and instead of looking at large scale by making a domain go to infinity, we are going to fix the domain and make the delta go to 0. So now let's state again the theorem. We stated it in 2 forms. It was an exercise to prove they're equivalent. We're going to do this exercise now. So the first form was that if you take a domain of the plane simply connected with 4 boundary points, and you ask what is the probability function of the delta, which is the size of the hexagons by which you discretize this domain. If you ask for the probability that there is a black path linking the arc AB to the arc CD, usually such a path is called crossing. So this quantity has a limit as the mesh size goes to 0. The limit is a function of the domain and the 4 points. And this f is conformally invariant, which means that if phi is a conformal mapping from a domain to another domain, which sends A, B, C, D to respective images A, B tilde C tilde D tilde, then F omega A B C D is the same as F omega tilde A tilde B tilde C tilde D tilde. Informally, we would like to say that, you know, if we apply a conformal map to a domain and send it to another domain, the limit of percolation in that domain should be the same as the conformal image of the limit of the percolation in this domain mapped to that domain. Okay. So it can be, one can make sense of this. What we make sense of is the fact that the limit of a certain probability, the probability of a black path linking two arcs, behaves indeed in the way we would expect to behave, assuming we have this conformal invariance. Again, I assume that you've seen conformal invariance in the talks of Vincent, so I won't define it in much detail. Okay, so plus there was something remarkable. So that's the Cardis formula, that F on a triangle like that with marked points A, B, C, D, function of A, B, C, D, has an explicit formula if the triangle is equilateral, and it's what? It's just D minus C over A minus C. Okay, so it's a quantity that goes to 1 as D approaches A, goes to 0 as D approaches C, as it should, and it's linear in the case of an equilateral triangle. So that was the first form. Let me now state a lemma which we are going to use. It's not very difficult result if you have the Riemann mapping theorem. It says that for any domain omega A, B, C with 3 marked points, there exists a unique conformal map that sends omega to this equilateral triangle, and any equilateral triangle, and A, B, C to the vertices of the triangle. Okay? So proof, well, it's Riemann mapping theorem. Rephrased in a certain way. Of course, you should prove separately existence and uniqueness, and well, both can be proven using the fact that we can map already omega to this domain, and then that we have 3 degrees of freedom, 3 real degrees of freedom in the choice of the conformal map that allow us to precisely choose the targets where A, B, C get mapped to. Notice you cannot send 4 points to a square. Okay. It's only 3 points because the map is already unique once you fix 3 points. So from there, from this lemma, we can make a remark. Gives a formula for F omega A, B, C, D, provided we can compute map omega to the triangle and A, B, C to the vertices. Yeah. D will get mapped somewhere. You don't have the choice as to where, and you'll be able to compute this function by computing it on the triangle as explained here. Is it clear? So the second form of the theorem of Smirnov, so let's call it theorem prime, is a bit more specific, and it really shows that complex analysis is the main player here. So the result is that if you define three functions, so define HA, HB, HC, they're all functions of delta also, okay? But I usually will omit this. Here I will not omit. And so what is the definition? HA delta Z is the probability that in your domain that has three mark points A, B, C, for a given point Z in the bulk, you have a black path that separates A and Z from B and C. A, Z separated from B, C by a black path. Okay. So you have this function, which is a function of the point and of the domain. And you have similarly two other functions, HB delta, HC delta, defined symmetrically. I defined that last time, so I won't rewrite them. Just to say in words, HB delta Z is the probability that there's a black path separating B and Z from A and C. HC is the probability of having a black path separating C and Z from A and B. Okay, so the theorem said the following. Gave two convergence results. The most interesting one is that HA delta plus E 2 pi I over 3, HB delta plus E minus 2 pi I, 4 pi I over 3, HC delta, so function of Z, converges uniformly on compacts, and even more than compacts if you wish. Converges as delta goes to 0 to phi omega to triangle, where phi omega to triangle is the unique map from omega A, B, C to the triangle with vertices, triangle delta with vertices 1, E 2 pi I over 3, E minus 2 pi I over 3. Or if you wish, this theorem gives a new proof of the Riemann mapping theorem. It tells you that you can construct this conformal mapping as a limit of three probabilities. Okay? And the other convergence result is that HA delta plus HB delta plus HC delta converges uniformly to 1 for every Z. Okay. So the question was, why does this theorem imply that theorem? Let me write a theorem prime very quickly, which makes just the algebra a little easier. It's by no means different than theorem prime, but it just makes the calculations a little easier. The statement is H A delta plus I over root 3 HB delta minus I over root 3 HC delta converges to the map to phi sending omega to new triangle, and this new triangle is has vertices 1 I over root 3 minus I over root 3. So it's just a rescaling, of the, the first theorem is about convergence to a triangle spanned by the roots of unity, and the other one is to an equilateral triangle with one side living on the imaginary axis. Just, and HA plus HB plus HC delta converges to 1. Okay. So, that theorem, this theorem and that theorem are completely equivalent. For this function is 2/3 times that function plus 1/3 times that function. And it's just a linear mapping of the first of this one, of this triangle to that triangle. So this is completely equivalent to that. It's just a little easier to work with that. So now let's see why theorem prime prime implies theorem. Okay. So why is it true? Well, so we have a domain omega A, B, C, D. We have a way to map it to this triangle with vertices 1, I over root 3 minus I over root 3. Okay? Now, if we consider a conformal map, so this is called phi omega to triangle prime. Now, if we consider a conformal map, say psi, that sends our domain to another domain, A tilde, B tilde, C tilde, D tilde, the points, and the domain is omega tilde. This is omega. Then we also want to consider the map phi that sends omega tilde to the triangle prime and sends the right points to the right point, A tilde, B tilde, C tilde to the right points. And so observation, it's easy. It's that the mapping here is the same as the composition of these two mapping. So phi of omega prime, phi of omega prime goes to delta prime is equal to phi of omega go to delta composed with psi omega to delta prime is the same as the map from the map psi post composed. It's always hard with compositions with the map from omega tilde to delta prime. Okay. So this is uniqueness. Both are conformal mappings, and they both satisfy the same boundary conditions. They send the 3 points to the 3 points, so they are the same. And what can you do with that? Well, now we take real part of phi omega goes to the real part of this gives us, well, what is the real part? Well, these guys are purely real. They're probabilities. So there's only this guy left. So it's the limit of H A delta. Okay? So what we have is that H A delta is a conformal invariant. Because if you compute H A tilde here and H A here, H A here can be obtained by composing psi with H A tilde. Because we have uniqueness of the map phi, and because H A is just the real part of that map. So H A delta Z is the conformal invariant. And now the only thing that is left to do is just bring Z to the boundary. Now bring Z to the point D. And you have exactly what you wanted. Is it clear? Is it convincing? Why these theorems are equivalent? Again, what we have is that we constructed out of this combination of three probabilities a conformal mapping. Now we know conformal mappings are unique. Or once you choose the right boundary conditions, but we have them. Okay? So now what you can do is say, okay, let's just look at the real part of this conformal mapping. And this real part is just the scaling limit of a probability. So scaling limits of the probability HA are conformally invariant in the sense we want, because conformal maps are essentially by construction and uniqueness conformal invariant. So we have proven that this statement for a point Z that is allowed to live anywhere inside. Now you bring Z to the boundary and you obtain the first result. So the second result is stronger than the first result. It's actually a bulk generalization of the first result, if you wish. Okay? So, okay, now we need to prove something about percolation to prove theorem prime prime. So, proof contains three main steps. The most interesting one is the last one, but the other ones teach us a lot, and they are certainly necessary to be rigorous, but they also teach us a lot about what happens. So the first, as often in convergence result, is a precompactness result. The second, so we want to make sure that as we are making this process delta go to 0, things are controlled. Probabilities are under control in the sense that they will not depend too much on the position of D. They will be essentially continuous with respect to Z, uniformly with respect to all the scales, or the mesh size delta. So we need this precompactness result. Then we need to identify boundary conditions. Then we will need to prove analyticity. Well, and then we need to make a conclusion. We need to conclude from the things we'll have proven. Okay. So what does it mean? So it means that we really want to prove, that this function HA delta plus I over root 3 HB delta plus minus I over root 3 HC delta is uniformly precompact with respect. It forms a uniformly precompact family with respect to delta. The scaling limits, well, the scaling limits along subsequences that you obtain by the first step will satisfy some reasonably obvious boundary conditions. And the key point is the analyticity. The fact that if you have a scaling limit along subsequences, it is analytic. After these two steps, you still have an infinite dimensional family of possible limits, but the analyticity will show you there's just one. So that's really the strong part, and that's really the part that allows us to really connect what happens with percolation and what happens with conformal invariance, what happens with the scaling limit. That's the part where we actually can say we understand what happens precisely. Okay, so that's the strategy. So let's start with the precompactness. Okay. So again, we want to show that this family of functions indexed by delta is uniformly continuous. Actually, it's a uniformly Hölder for a certain Hölder exponent, which is certainly related to this alpha positive that we obtained here. Okay. So want to show H A delta family of functions of z, okay? Family of functions indexed by delta is uniformly Hölder, alpha Hölder on compact sets. Actually, it's a bit more than that. You can extend the precompactness to the boundary if the boundary is not too awful, and you can extend it to the boundary in any case. You would just have to change a bit the definition. Well, you'll see what happens. Nothing crazy happens. Well, okay, I want to make a true statement, and that's a true statement. So, of course, HA, HB, and HC are symmetric of each other. So, HB delta and HC delta, the same thing. Huh? If I can prove that the first one is uniformly Hölder, the whole linear combination is going to be uniformly Hölder continuous. Okay, so how do we prove that? Well, how do you prove that something is continuous or uniformly continuous? Well, you just ask the question. Well, what happens if I look at the values of the function at 2 points that are close to each other? Okay. So let us compute or estimate. Estimate H delta z, HA delta z, sorry, and HA delta z tilde for z tilde close to each other. Well, I can just add an easy comment. This family of function is obviously bounded because the HA, HB, and HCs are all probabilities, so they are between 0 and 1. So there is no question about boundedness here. Huh? So okay, let us estimate this. So I will use a trivial inequality in probability, but if you completely trivial, but if you've not seen it, it might make it a bit hard to follow the thing. So we are going to use the very elementary inequality, probability of A minus probability of B is probability of A minus B minus probability of B minus A. That's really the thing we're going to use. And we can also say that in absolute value, this is going to be bounded by probability by probability of A minus B plus probability of B minus A. Okay, that's really trivial, but somehow, yeah, it's not necessarily an inequality one has seen used all the time when studying undergrad probability. So let me just write it down. Okay, so now we are going precisely to compute this minus that, so it's a difference of two probabilities. So H A delta Z minus H A delta Z tilde. So what is it going to be? Well, we are going to say that it is smaller than the sum of probabilities of the corresponding events. So I'm going to introduce a notation. So it's going to be the probability of QA delta Z minus QA delta Z tilde plus probability of QA Z tilde delta minus QA delta Z. Okay, so where QA delta Z is the obvious event of which we are taking the probability. So the probability, so that's the event associated with the probability. So it's the event that A and Z separated from B and C, okay, by a black path. Let's make a small picture. What happens? let me just write. It should be obvious that HA delta Z is the probability of QA delta Z. So now we want to estimate this difference by estimating this sum. Okay, so here is the domain A, B, C, Z, Z tilde. Okay. So we are comparing the value of HA delta at Z and the value of HA delta at Z tilde. And so we have this inequality, and so we try to bound the probability of both events. So let's look at what this event means. Okay, what does this event mean? It means that something happened for Z, but doesn't happen for Z tilde. So what does it mean? It means that Z is separated, Z and A are separated from B and C, but Z tilde isn't. So, well, first, if Z and A are separated by a black path from B and C, it means that there's a black path somewhere. So now this black path can either pass here or there. But if it passes there, then Z tilde is also disconnected from B and C and is on the same side as A. But precisely in the definition of this event, it doesn't occur. So it means that the black path passes precisely between. Okay? It cannot pass here, for then Z tilde would also be disconnected. Moreover, if nothing happens for Z tilde, it means that there are not so many black hexagons around Z tilde. Otherwise, I mean, we said there's a path, but we also said there is no path separating Z tilde. What does it mean that there is no path separating Z tilde and A from B and C? Well, it's again this self-duality, which is not so obvious to prove, but fairly intuitive. That tells you that it means that there is a white path that comes and touches the Z tilde thing, and actually somehow, you know, maybe it does something like that. It at least, you know, it at least prevents Z tilde from being separated by a black path that would come somewhere. So, okay, so what does this picture mean? It means that probability of QA delta Z minus QA delta Z tilde. Well, if this event implies that picture, it means that the probability is less than the probability of having black path from a small circle of diameter Z minus Z tilde to both sides AB and CA, to AB and CA plus, well, and a white path from the same circle to BC. Okay? So it means there are lots of paths. Basically, this little circle here is linked to both these sides by a black path and to that side by a white path. So this seems fairly unlikely if Z and Z tilde are close to each other. It means that you've managed to connect a very small circle to all three sides. So I'm going to write it informally. At least one of AB, BC, and CA are far from the circle. Okay. So the idea is that, you could tell me, okay, if z and z tilde are just here, the existence of a black path linking z and z tilde to that boundary is not a big deal. It's very likely because they're close to the boundary. But at the same time, you would be far away from another boundary component. So since you have three paths linking all sides, you're at least far from one of them, wherever you are in this domain. So implies a connection of the type, which we can schematize this way, of a type a small circle is linked to a big circle. The probability thereof has been bounded. Bounded by, well, let me be loose, but the power alpha by RSW. Okay, I'm a bit loose here, but I hope you get the idea. So it implies that something, some small thing, if z and z tilde are close, is linked to a big, is linked at a large distance. So it implies an event of this form, and we have precisely explained why events of this form have small probability. Okay, so of course we have just bounded that event, but that event is the exact symmetric. Is symmetric. So we have finished the proof of equicontinuity. So HA delta is alpha Husserl on compact set. Again, if you introduce the proper metric, you can make it uniformly equicontinuous on the whole domain, but we don't really need this here, and we won't really enter the details. Okay, so that's the end of the first part. So, questions? Now let's just deal with the boundary conditions. So we need a statement about the boundary conditions, and it's going to be a nice statement. If you look at each by yourself, you will see that it's not very difficult, so I hope that following what I explained will also be easy. So boundary conditions, so two. The statement about boundary conditions is that any scaling limit, so we don't know the scaling limit exists, but we know there are scaling limits along subsequences because we have proven Husserl continuity, which means uniform equicontinuity, which means by Arzelà-Ascoli precompactness in the space of functions. So we can definitely say that as delta goes to 0, things are not too crazy. The worst thing that could happen to us is that there are several possible scaling limits, like a sequence of numbers in a compact interval. That's really the worst that can happen to us. So we can at least speak about the limit points. And we can, if we can prove the limit points are unique, we'll be done. So let's speak about the limit point. That's what I'm saying. Any scaling limit as delta goes to 0 of HA delta plus I over root 3 HP delta minus I over root 3 of HC delta is a homeomorphism from the boundary of the domain on which we are defined to the boundary of the triangle to which we want to map, and A, B, C are mapped to 1 I over root 3 minus I over root 3. So already we have something. At least it's obvious that if there is a there is a limit for the conformal map. It should be, there's an analytic limit, it's very intuitive, it should be the conformal map. At least on the boundary, it's bijective, it sets the boundary to the boundary, the correct boundary points to the correct boundary points. So, proof is not very difficult. I don't know how much detail needs to be given. So, if you want to prove such a thing, you can just first prove that the right segment of for instance, the segment AB gets mapped to the right segment here. Gets mapped to the segment. So, let us prove that AB gets mapped homeomorphically to the segment 1 I over root 3. Okay. So, what do we need for this to be true? We need continuity. We need to prove that the limit is continuous. We need to show that A gets mapped to 1, that B gets mapped to I over root 3. And we need to show some kind of monotonicity, that basically you're bijective, so yeah, you should be monotonous, because if you map a segment to a segment, that's what you should do. Okay, so let's do that. Very intuitive. So again, our domain is here, A, B, C. So now let's first ask, why does A get mapped to 1? Well, simply because the imaginary part is inexistent here. HB delta of A goes to 0, and HC delta the same. If you evaluate if you take the point Z to be next to A, and at the same time, HA delta goes to 1. So let's say that it is intuitive and it can be made rigorous with this RSW estimate. Okay. So let's see why it is intuitive. The easiest is probably this one. So you ask the question, what is the chance that Z equals A and A are both separated from B and C by a black path? Well, the idea is that there's going to be a black path of maybe a tiny size here. But since Z and A are so close to each other, there are infinitely many scales at which you could have a black path separating A and A from B and C. So the chance of having this separation tends to 1, intuitively. So again, it's not true exactly on lattice level, except if you take Z exactly equal to A, maybe on lattice level. It's not exactly true on lattice level, but we are speaking about a scaling limit that's supposed to exist because we have proven the precompactness. Okay, so we can say, okay, let's look at how things are for delta small, and that's how things are. So similarly for these two guys, why are they going to 0? Well, what is the chance that there is a path separating Z equals A and B from A and C? Well, since Z is next to A, the chance of being separated by a black path is essentially 0 if you want this black path to go up to B. That's the idea. Again, proving it rigorously, you just use Vertos-Hemel-Welch, and for C it's symmetric. So let's say it's intuitive, and the way to make the intuition rigorous is RSW. It's a good exercise. It doesn't leave much surprise, I would say. So you can go, you can prove it the way you would expect it to be. It should be proven, and that just works. Okay, so we have already mapped boundary. So we have mapped A to 1, and again for symmetric reason, B gets mapped to the endpoint. So now we need to prove continuity and monotonicity, and so these are also fairly easy. So continuity, I will go quickly because that's really not the main part of the theorem. The continuity is the same as the precompactness part. As I said, you could extend the precompactness, the alpha continuity to the boundary with the proper metric, and at least you are continuous. You just compare the chance for a z here and a z there, that there is a crossing for z but not z tilde, and you get something. And monotonicity is already true at the lattice level. Well, and the idea is, okay, if you take A, B, C, C and Z here and Z tilde there, the chance that this D is separated from B and C is clearly bigger than the chance that Z tilde is separated from B and C, because if there is a path separating Z tilde from B and C, it also separates Z. And conversely, it can be shown that with some probability, you have a path that separates Z but not Z tilde, and so you're strictly increasing. Again, you use RSW to be rigorous. Okay, so I wanted to go quick because I want to go to this part, analyticity. Okay, so I hope at least you have an idea of what happens for these two steps. But we want to show that the things behave nicely as the mesh size goes to 0 without saying too much precisely what the values are. We want to say that they are nice in the way they should, and it so happens they are. So, and that the way to make it rigorous is precisely this RSW estimate, which allows you to say things, uniformly with respect to the mesh size. These estimates are fairly weak, but they're strong enough for our purpose. Okay, analyticity. So, what is an analytic function? So, an analytic function, the way we learn it in school is that it's a function that can be expanded into power series, and that's a valid definition. That's not really what we want here. For us, analyticity is going to be holomorphicity. I mean, both are equivalent in the complex plane, of course, but one is more suggestive than the other. And so what is a holomorphic function? It's a function that's complex differentiable. What does it mean? Really local. It means that locally at every point, your mapping, if you Taylor expand it at first order, looks like a composition of a translation, a scaling, and a rotation. Okay. Well, basically, these are the operations you can do by adding and multiplying complex numbers. So the fact that you're complex differentiable really means that locally you are like scaling, a rotation, and a translation. So how are we going to be able to extract some information from that function to make it say that at least as delta goes to 0, it's going to be holomorphic? That's the question. And so the way it will go is as follows. We will get some discrete identity on the lattice level, combinatorial identity. And this discrete identity should be interpreted as an analog of the Cauchy-Riemann equation, a discrete analog of the Cauchy-Riemann equation. Cauchy-Riemann equation is, Cauchy-Riemann equation is just, you have, there are many ways of writing it, but if you say that f equals I plus g plus ih is holomorphic, it means that del x g is equal to del y h, and that's the real and imaginary part, and del y g is equal to minus del y. So, that maybe doesn't look completely obvious, but it just means one thing. It means that your derivative map, viewed as a map from R2 to R2, if you view the plane as R2, is just a composition of a rotation and a scaling. So it just means your discrete holomorphic. Well, it means that there is a relation between real part and imaginary parts also, and obviously. And so that's exactly the kind of analog of, we would like exactly this kind of things on the lattice level, because this looks like a real part and this looks like an imaginary part, of course, of the function. So we would like to have some, identity on lattice level, which will use really the definition of the model, that it's the triangular, the critical percolation on triangular lattice, and which will tell us that the limit is what it should. So, what is this? What is this thing we're going to get on the lattice level? So let me make a picture and state this fundamental result. That's really the key here. So it's lemma. Discrete Cauchy-Riemann. Well, before maybe stating the lemma, I want to state it, but leave some space to guess what we should kind of get. So to get the lattice identity, we should look at the lattice. So let's really look at the lattice level, what we get at the lattice level. So let's draw some big hexagons. So now, we didn't really need up to now to say on which lattice or function is defined. In some sense, it's defined everywhere. And in some sense, it doesn't really matter where it is defined. No, because we take the scaling limit. But now we really want to have something combinatorial on lattice level, so we need to say where our functions are defined. And so the functions HA delta, H delta, HT delta, they're going to be defined on the vertices. I mean, you're free to extend them as in the way you want to other points, but our focus is going to be on the vertices, okay? So defined on the vertices. Now, what could be the analog of a derivative? Well, a difference, of course. So for an edge xy, an oriented edge, okay, from x to y, I'm going to denote in a function f, defined on the vertices to C. I'm going to denote by del sub E of f the difference. Okay, that seems reasonable. So we would like to have an identity, so saying something about the discrete derivatives, the difference of the functions h, a, b, c. And so now these functions h, a, b, c are themselves probabilities of things, and we are very tempted to use this identity that the difference of probabilities is the difference of probabilities of events. So we'll write define. I'm going to define the positive part del of HA, for instance. So what is going to be the positive part of the derivative of HA at this point? It's going to be defined as the probability. What would you like to say? The chance of, it's a probability here minus probability there. So it should be a probability of an event occurring here but not there. So that's exactly what I want. So QA delta y minus QA, that minus QA delta x. Okay. So this guy is a positive guy, as it should be. It should be a positive part. So it's a positive guy. So it's just chance that the event associated with HA occurs here but not there. And okay, well, so guess the rest of the notation. That's the exercise. I mean, it's really an easy exercise. Of course, I'm going to do the same for HB and HC. I'm going to just replace the A and by B and C, and I'm going to define a negative part by just swapping these things. Anyway, I don't need the I don't need the negative part at this point. At this point, I just need to the positive part for the lemma. So the lemma, I'm going to write it. It's D. I'm going to write it in a schematical manner. So let this, and this be three oriented edges with the same origin. They start from the same x, but they go at these 3 points. Origin, okay, with the same origin, and well, in a counterclockwise order. And again, the notation is obviously suggestive that this is going to be the first, the second, and the third. Okay. So the identity is that del plus of HA delta is equal to del in the opposite direction, I mean in the 120 rotated degree direction of HB, and is also equal to this guy. Okay. So that's the identity. I'll need 5 minutes to prove it, so it's going to be hopefully fine. So next time we should just finish and explain why this implies analyticity. Okay, but no, I'm not done yet. I just want to prove this identity today. So let's finish the proof. It's a really beautiful combinatorial proof. So let's just make pictures. The idea is that, you know, each of these 3 terms is a probability of something. Okay. Well, this one I wrote, and the other one is the same with B, and the third one with C, and the edges are rotated each time. So there are probabilities of events. Now how are we going to prove that probabilities of events which are obviously different, these events are different, are the same? Well, we are lucky. We're working with percolation, so you know, if you describe an event, a configuration by the collection of all the blacks and the whites, essentially each configuration has exactly the same probability as the others. So if you manage to construct a bijection, mapping the configurations associated with one event to the configurations associated with another event, well, you prove that both events have the same cardinality in the space of elementary configuration, and because all probabilities have the same chances, because you're working with critical percolation, then the chances are the same, so the probabilities are the same. So, so that's the idea. We want to construct bijections. Let me just make a picture to explain how it's going to work. So let's compute the first positive part of the discrete derivative. So I draw here 3 hexagons where things happen, and the points on the boundary are A, B, C. So what's going to happen? So this point is going to be separated together with A from B and C, but not that point. So it means there is a black path passing here. Okay. And not there, because otherwise that point would also be separated. Now, the thing is that we can already say what is the color of this hexagon. It's not black, because otherwise this black path could just be extended to separate the origin. So this hexagon is white. But this hexagon is white, but in the hexagons that surround it, at least one of them is white again. Otherwise, there would be a black path surrounding and separating this origin. So you have a white hexagon here, and it's connected to another white hexagon somewhere. And you can keep going, otherwise you again would be separated by a black path somewhere, and you end up reaching this part. Okay, so what you see in this picture is something that's fairly symmetric, with 3 hexagons centered around the origin of the common origin of the edges, and what happens is that 2 of the hexagons are connected by black path to 2 arcs at the boundary, and 1 hexagon is connected by a white path somewhere in the boundary. And so now, let's just make the picture. So that's del HA delta. Okay, that's the del H delta is plus. Sorry, that's the event of which we are computing the probability. And so now let's see what is the other del. Del this guy HB delta. What is this? Let's draw again, same hexagon, same domain, same hexagons. What does it mean in this case? Well, it means this point is separated, no, this point is separated, but not that one. Okay. Something occurs at the end of this edge, but not at the origin. So, what does it mean? It means we have a black path. Where does this black path go? Well, it separates B and the points from the other points, A, B, C. So you have a black path here. For exactly the same reason as before, you have a white path there. So, you know, this looks similar. It looks symmetrical. Obviously, the events are not the same, but something very similar is occurring. So the proof, so we want to construct a bijection. Almost. A bijection between these events, the configurations associated with the events, okay? These events. So, well, obviously we need to flip some colors. The colors are not the same, so we need to flip some colors. What is this bijection? Let me just draw a picture to describe what the bijection should be doing, and then I'll leave it as an exercise to convince yourself that it can be done. I mean, it works, it's bijective. So, the bijection will do something as follows. So, you have, very schematically, you have something like that here. And then what you're going to do is flip some colors and get something like that. Well, no, but this you can do, but not the one I want to do. I want to do the other one. This way. So you're going to be able to somehow flip the color of this guy in a bijective manner. And then we'll flip all the colors of everything at the same time, simultaneously. That's an easy bijection. And we'll get something like that. It's exactly this guy. Okay. So that's a global color flip. That's obviously a bijection. That thing where I switch the color here is not obviously a bijection. So how should I do it so that it's bijective? So I want to do a mapping that will do that, and it's invertible. I can just do something, and just if I want to say undo, I can undo on the picture without. I mean, I can just go back without having destroyed any information. So the idea is hard to write, but it's easy to explain. Is you should take, you know, this path is not unique a priori. There could be several choices of path. The hexagons the structure is a bit messy. You could have a lot of random things that allow you to choose several paths. But you can choose here you can choose the counterclockwise most path, white path. And here you can choose the clockwise most path. Yep. And what you can do is you can flip the colors of all the hexagons that are not these two things, but that are strictly contained in the region delimited by this path without flipping the colors of this path themselves. This way, the counterclockwise most white path is still there, and the clockwise most black path is still there, but you effectively flip the color of the guy that was inside. And so it's bijective, so that's what happens. And that proves exactly that the number of pictures here is in bijection, is the same as the number of pictures there, because they're in bijection. And so that proves this Cauchy-Riemann identity. Okay. So now there is some work to prove that this actually allows you to is the proper representative of this. But we somehow can forget about speculation now. It's just a matter of, you know, showing that this kind of identities allows you to do this kind of job. Okay? Clear? So that's it. Sorry for being late. Question?